Yeah, thanks, Tim. So this talk introduces improved scalability for key-value stores. We focus on stores that run on a single multi-core machine, which are nowadays common in production settings. And these are often used as the basic building blocks for distributed databases. Our goal is to scale up this single store by maximizing their parallelism. I guess this is the reason why we are in this session and not the key value store session. So as many of you may know, in recent years, big key value stores managing billions of items are prevalent in serving big web scale systems such as indexing web search engines and serving personalized media. And key value stores are essentially a persistent map supporting atomic put and get operation. Modern key value stores also support range queries and snapshot scans. Key value stores are commonly implemented as log-structured merge stores, LSMs. For example, this includes Apache's HBase, Google's Bigtable, Yahoo's Peanuts, and the recent popular LevelDB and its extensions HyperDex and RocksDB by Facebook. Before I dive into the details of our algorithm, I want to go briefly over the main principle at the base of log-structured merge store. So an LSM organizes the data in a series of components of increasing size. The first component is a memory component, CM, which holds the most recent data. The rest of the component reside on disk. Major building block is the merge or compaction procedure, which incorporate the content of each component into the next one. In the context of our work, we perceive all the disk component as a single component CD. So a core property of LSM stores is absorbing the write in the main memory component and merging them into the disk component when it is filled. This approach masks disk access latency from the application and allows to improve throughput by performing sequential I/O. Read operation, get operation, access both the memory component and the disk component, and in case the workload is queued with high locality, the access hits the cache most of the time. So this is a simpler view of a log-structured merge store. The right access the insert items into the memory component, and when it is filled, it is merged into the disk component. Upon merge, the memory component becomes immutable, and a new CM component becomes available to serve new updates. This picture would not be complete without mentioning that write operation also log their updates in write-ahead log on the disk, but a standard configuration for this is to do asynchronous logging, which means the access to the disk happens at the background. So read operation, while write operation access only CM, read operation access all active component. If get operation fails to find the key in the current memory component, it searches for the key in the previous memory component and then at the disk, again hitting the cache when the workload is skewed. So I'd like you to remember this order of access component because we'll get to it later on. Put, get, and merge operation all access the component through a global in-memory pointer data structure, where PM points to the current memory, PM tag points to the previous memory, and PD points to the disk component. So the major bottleneck of current existing key value store is their limited in-memory concurrency. And the challenge this system faces is how to scale up with available hardware resources, and specifically with the number of CPU cores. It seems that the key for scalability is the synchronization around this pointers data structure. Our solution, cLSM, can be pronounced as cLSM, provides a light synchronization for accessing read and write access of this pointer data structure. So first, we assume a thread-safe implementation of the memory component. This takes care of the per-component synchronization, and there are many off-the-shelf efficient implementation of such data structures. Second, we add a shared exclusive log to protect the pointers. So how does it work? A merge operation takes the lock in an exclusive mode to update the pointers before and after the merge occurs. A get operation, a put operation locks takes the lock in a shared mode just during and it is blocked, maybe blocked, but just during a very short period before and after the merge. But several put operation can proceed concurrently. And finally, a get operation need no synchronization, doesn't take the lock. And note, if you remember, the order in which get operation access the memory, the component, the different component of the system is similar to the direction which the data flows, and is the opposite of the direction where you update the pointers. So worst case scenario, a get operation needs to scan the same data twice, which might be inefficient but is still correct. And we get to avoid the lock. cLSM also supports consistent snapshots. LSM stores that support snapshot usually use the common approach of multi-versioning. And we add a counter to manage the versions. A put operation increases the counter, and when a scan is initialized, it reads the counter. And the next operation of within a context of a scan returns the most updated version that has timestamp that is smaller than the timestamp that is associated with the snapshot. So, but we need to be careful, because there can be races between the put operation that updates the updated clock and the scan operation that reads it. For example, consider two concurrent put operation. The first increases the timestamp to 98, and the second increases it to 99. And a snapshot operation acquires timestamp 99. Now it returns, it misses the value that is written by the first put, and it sees the value written by the second put. Whereas an earlier snapshot that acquired the timestamp 98 sees the value that is written by the first put operation, but it filters out the value written by the second operation. So this scenario violates serializability, because there is no consistent way we can serialize the two snapshots. In order to avoid it, we manage an active set of pending put operation that have already acquired the timestamp but have not written yet the data to the store. So in our example, the first put operation would add 98 to the active set. Both snapshot operation would see this in the active set and would acquire the maximum timestamp of 97, and therefore they wouldn't see both the two values written by both put operation, and their results are consistent. But this is still not enough, because acquiring the timestamp and adding it to the active set is not atomic. So there can be a case where the snapshot operation sees the timestamp by the put operation, but it misses it in the active set, and therefore it sees the value written by this concurrent put, and this brings us back to the problem of the previous slide. So we do take care that to make sure that snapshots are, that put operation are aware of concurrent snapshot operation, and in case a put operation noticed that its timestamp was missed by a concurrent snapshot, it restarts and acquires a new timestamp. And there are more details in the paper. Read, modify, write operation. We also support, cLSM supports it in an efficient way that avoids blocking. At this point, we have an additional assumption that the data structures support implementing the memory components is based on some linked list implementation, for example, skip list, which is actually often the case in real systems. So we now apply optimistic concurrency control. We access both the memory component and the disk component to find out the last version of the item, and we install the new version in the memory component using an atomic compare and swap operation. Failure of this operation indicates that there is some conflict and the operation restarts again. But note that this time we don't need to access the disk, because the disk values are already known to us. So we just need to do the operation again in the memory until we succeed to install the new version. Okay, we reached the evaluation section. We implemented cLSM based on the LevelDB. We replaced the lock with our light synchronization mechanism. And we used some libcd data structured library to implement the memory component. We ran our experiment on a machine with 16 hardware threads. Our data set was 150 gigabytes of size, and we allocated 128 megabytes of memory to the memory component, which is the default value in the systems like HBase. And we compared our implementation with state-of-the-art existing systems. We configured RocksDB to use only a single thread for compaction, because we wanted to compare the memory behavior of the different systems. So this is the first, we first explored the 100% write-only scenario, where the keys are drawn uniformly at random from the entire range of the keys. You can see that both RocksDB and LevelDB have limited scalability due to their single writer architecture. HyperLevelDB gains have 33% throughput gain at 4 workers, but deteriorates beyond that point. cLSM gets 2.5x throughput with 8 cores. The reason for the small degradation of the cLSM throughput might be due to cross-chip latencies and cache invalidation. We continue with read-only workload. Here we used a skew distribution, where 90% of the keys were chosen from popular blocks comprising 10% of the data, and the rest are selected uniformly at random. Here you can see that HyperLevelDB and LevelDB scale until 8 threads. This is probably due to the fact that they're synchronized, they're blocking even when the data is available in the memory. Both RocksDB and cLSM scale all the way through to 128 threads. However, RocksDB's performance is actually slower even when compared to LevelDB. We believe that the performance results for cLSM are due to the fact that get operation never block and they're essentially lock-free. We also did mixed workload experiments and experimented with production workloads, and the results are in the paper. For read, modify, write, we used put if absent flavor operation. And most existing systems do not support read, modify, write as a native operation. Therefore, we augmented LevelDB with a textbook implementation of read, modify, write using lock stripping. As you can see, cLSM throughput is 2.5x better than the baseline. We also experimented with a workload of one-to-one scan write mix. We used the size of the range queries we used is between 10 and 20. And since we wanted to balance the number of keys that are being read and the number of keys that are being written, the number of scan operations that are executed is an order of magnitude smaller than the write operation. And the throughput is measured as the total number of keys that are accessed. As you can see, the cLSM performs better than the competitors. Okay, to summarize, leading key value stores rely on LSM data stores to serve their requests mainly for memory. cLSM is a new approach for scalability, for improving scalability based on by exploiting multicore hardware. This is why we tend to call it vertical scalability. cLSM overcomes scalability bottleneck by eliminating blocking during basic operation. Get operation never block, and put operation only block for short periods of time before and after a merge operation. We support rich API, including consistent snapshots and read, modify, write. cLSM is generic, which means it can be incorporated into a range of existing implementation, and it can benefit from optimization of other components of the system, for example, the compaction policies of RocksDB. And we believe it can serve as an alternative, or at least be combined with the common scalability approach, which is partitioning, namely horizontal scalability. Thank you.
Okay, questions?
Hi. Maybe I misunderstood something, but you mentioned that you have an on-disk write-ahead log. If it's a true write-ahead log, you mentioned that you also have an on-disk write-ahead log.
Yeah.
If it's a true write-ahead log, writes have to be synchronous. So the overhead is going to dwarf all this, right?
Yeah. So what I said also is that the common configuration is to use asynchronous logging. This means that indeed you may lose some data, but yeah, usually this is the case. It works. This is how the way the system works.
Thank you.